This program is about quadratic functions. Quadratic functions, we studied quadratic equations earlier in the year. This will involve an x and a y, and so that's what turns them into quadratic functions. We also call these parabolas. You can see the basic parabolic shape down here. The simplest parabola, y equal x squared. We'll be looking at two forms of a parabola, the standard form and the general form. The standard form of a parabola is f of x, or y, is equal to ax minus h squared plus k, in which case the vertex, now I'm going to be referring to the vertex generally as x vertex, y vertex, but if you can get your equation of the parabola into the standard form, then your vertex is just hk from the standard form. You can also look at this, if you want to relate it back to the equation of a circle. You recall the circle had the equation x minus h squared plus y minus k squared equals r squared. Here there was an x minus h and a y minus k to give you the hk. You can think of the parabolic equation in the same way with an x minus h and a y minus k. If you bring the k over to the other side, then it reads y minus k equals a x minus h squared, and you can remember this formula in either form. It really doesn't matter. The second form we'll be dealing with is the general form. You've seen this before. The general form is f of x is equal to ax squared plus bx plus c equals f of x. F of x, of course, is the same as y, and in order for this to be a quadratic function, we must have that a is not equal to 0. So that's f of x, or y, is equal to ax squared plus bx plus c. The vertex in this case, x vertex, y vertex, is given by x vertex is found by putting negative b over 2a, and y vertex is just f of x vertex. Now let's talk for a second about this constant a. It exists in both forms, a here times the x minus h squared, a times the x squared here. That a is a very important constant. It tells us a lot about the character of a parabola. If a is greater than 0, then the parabola opens up, which means it looks like this. Now when a parabola looks like this, it has a relative minimum. Its relative minimum is also its absolute minimum, and it is at the vertex. Recall that a parabola is symmetric, has a symmetry line through it. Where the symmetry line meets the parabola, we call that the vertex. And we'd say the minimum is y vertex at x vertex. What is the minimum? Y vertex. Where does it occur? X vertex. Now similarly, if a is less than 0, the parabola will open down. If it opens down, it looks like this, and instead of a relative minimum, then it is going to have a relative maximum, and we would say the maximum is y vertex at x vertex. A little bit less important, but still a significant property of a is as follows. If a is a number in size greater than 1, then the parabola is going to be taller. So we would call it narrow. Remember? Tall and narrow are the same. Now, narrow relative to what? Well, narrow relative to the standard parabola. So if a is 2, the parabola is going to be twice as big, twice as tall, and that's going to make it appear to be negative. For example, instead of when you get to x equals 2, y being 4, when you get to x equals 2, y will be 8. So the parabola is going to go through those points, and it's going to look like this. So when the absolute value of A is greater than 1, you have a narrow parabola. When the absolute value of A is less than 1, you have a wide parabola. If at 2, if A was 1/2, at 2, instead of the parabola being 4 high, it would only be 2 high. It would only be half as high, so it would give you the impression of this wide parabola. Now, what it really is a short parabola, but short and wide are basically the same. So A is very important. If A is a positive number, the parabola is going to open up. If A is a negative number, it's going to open down. If A is a big number, bigger than 1, either positive or negative, doesn't matter. Negative would just make the parabola open the other direction. If it's a big number, it's going to be narrow because it's tall. If it's a small number, it's going to be wide because it's half as tall. That is, it's short. So short and wide are the same. Okay, let's try out one. We'll take first off a problem where the parabola is in standard form. It says graph y equals 1/2 x minus 3 squared minus 4. Now the standard form is, looking up at the top, y equals a x minus h squared plus k. So I've written that down here with empty holes for the h and the k. This is exactly the standard form, so I'm going to match this top equation right here to my standard form. So to get x minus 3 squared, I would just put a 3 here. To get y minus 4 here, this is a plus k. So I have to put negative 4 to get y minus 4, which means h is equal to 3 and k is equal to negative 4. So I have a parabola whose vertex is 3 to the right and 4 down. Now I number my graph here, 3 to the right, 4 down, so that would be right here. Well, that's approximately right. I might be off a little bit. 3 to the right, 4 down, and 1 point on the parabola is not going to do it. I need at least, say, 3 points on the parabola. Now, what that does is that establishes the symmetry line of the parabola. There's its symmetry line. Right there, 3 to the right. The line x equals 3 is the symmetry line for the parabola, so the vertex is going to be somewhere along this line. Our k is negative 4, so our vertex is right here. Now we need another point to be able to finish this parabola, and an easy one to find is the y-intercept. Now, of course, if my vertex was on the y-axis, I'd need a different point. But my vertex is off the y-axis, so the y-intercept may do the trick here. To get the y-intercept, set x to 0. And you get y equals 1/2. 0 minus 3 squared minus 4. Negative 3 squared is 9, so it's 1/2 of 9 minus 4, which is 4.5 minus 4, which is 1/2. So we have a y-intercept of positive 1/2, so that would be right up here. Now, since this is a symmetry line, we'll have another point the same distance away on the other side of the symmetry line, so that will put a point right here, and now we can sketch in our parabola, and there we have the graph of the parabola. Now, if the 2 points had been closer to the vertex, as they will in the next example, we would have needed additional points on the line, and I'll show you how to get those in the next example problem. Let's flip over to the